In this lecture, we're going to start building up our tensor notation that'll be used, of course, to represent materials properties in a mathematical way. So let's build up some notation here. I'm going to have Cartesian coordinate system, and already you'll notice that we're going to start representing our axes instead of X, Y, or Z, or A, B, C, or anything like that. We're going to be very careful to start labeling those X1, X2, X3, because of course then all of the directions can have a subscript. So xi refers to any one of these, I equals 1, 2, or 3. So already we're going to be off to a good start. Now let's look at the property that may exist in the material. So let's imagine this guy coming out here, and this is some property P, okay? And that property P is sitting there in the material. It's got a vector P, but I want to think about that in the sense of the Cartesian coordinate system. And because, as we explained in the last lecture, we're going to assume linear behavior and all sorts of things like that, then what we're going to do is say, aha, there is a component P1 along x1, a component P2 along x2, and a component P3 along x3. Now, if let's say, for sake of argument, that I want to build up a response. So let's pretend this is not a property now, but let's pretend it's actually an applied force. Because remember, this vector notation is generic, right? So if it were an applied force, I can do the same thing. And the whole point of this linear stuff that I was just talking about is that the displacement is going to be proportional, linear, to the force. So if P is a force, then I could have some other response we'll call Q. And Q can also be broken down into various components along 1, 2, and 3. So we won't get into that yet, but let's just write out then what we can do mathematically now that we have not labeled these A, B, and C, and we've labeled them with these little things. We could say, well, let's assume that the Q can also be broken down into the 3 directions, and that it would be in each direction, like say Q1, that Q1 could be a response of P1, P2, and P3, right? So, and it's completely generic, right? It's just saying I apply this P in the material, it puts some sort of force all over the place. I get some Q out, but I want to think of Q in each one of these directions too. And so to be completely generic, I have to say, I'm not exactly sure Q1 is getting contributions from any of these components. And so to be completely general, I actually need to say that Q1 is proportional to P1, some fraction of P1, plus some fraction of P2, and some fraction of P3. You can already see what I've started to do here. So first of all, so each one of these is a coefficient that relates simply the effect of one of the P3 components, one of the forces, right? P is a force of some sort. And generically, we have these constants of proportionalities between Q1 and the components, right? So, of course, I can write this again for Q2. The response in Q2, and to distinguish this because that's a unique situation, I'm looking in the Q2 direction, yet I'm looking at the contribution from P1, so I have to change the notation. So the notation here, remember, it's 1, 1, because it's the effect of P in the x direction on Q in the x direction. So this is like, if there's no other contribution from anything else, we're completely linearized and P follows Q. This is what we're used to writing. But there could be contributions from the fact that I have this force going in the y direction, and that force in the y direction could cause a response in the x direction. And so that is related to A1 too. And then finally, same thing with z. I could have the component of P going in the z direction, and that actually could send something along a response along the direction of Q1 in a completely generic way. And so I have to, each one of these coefficients is the coupling, if you will, of these components into Q in that direction. And so we can continue to write that here. So there you have it. Now, our first big jump is to say, well, that's a lot of writing, and you can see it's getting pixelized because a lot of drawing on the screen now. So we could write this in a short form as just saying that whichever component, 1, 2, or 3, which ith component, is the sum of 1 to 3 of A times P. So for example, you would say for Q1, I equals 1. That means this is 1. And then J is the sum to 1, and I'm going to rotate through, right? So just to, maybe I should write that out. So actually, first let me circle this because it's an important relation. It's part of the way we're going to go here. And let me give you an example of Q1 would be, for example, the sum of 1 to 3 for J, and I is fixed now to 1, so this would be a 1, and then J would be cycled through, and we would do it for each one here. So you can clearly see how this becomes that, because I have a Q1, and then put the 1 there. So the first one is going to be 1, 1. And you see here 1, 1. The second one will be 2, 2. You can see 2, 2, right? Now, just to make it, when you do this a lot, people get tired. And so this is the part that confuses many students, but it's called the Einstein Convention. And you get tired of writing this sum. And you can see that it is a bit redundant if you do this day in and day out, trying to do general relativity evidently. So you get tired and you say, all right, look, there's a J here and a J here. That means that I'm summing because, that's the same thing. Every time one of these things appear, I have a repeated notation there. So because of of this and this, the sum is implied. So I don't need to actually write this down every time. So I can say Qi equals A I J Pj, and that's the same thing. The J's tell me that there's a sum out front. One thing you can do is sort of actually continue to, every time you see two subscripts next to each other like that, JJ, actually throw in the sum sign, write it, so you can, clearly see what's going on. And after a long time, you'll get tired of writing it and you'll just recognize that that's the case. And that's one way to get used to that kind of notation. So a repeated subscript has an implied summation. So just to finish with a crazy example, in a complete triclinic elastic material or something like that, where you have all the components around and there's no symmetry helping you out, you could have some Aij, which has 4 indices, right? And uh, you have A I A J J big J A K big K and A L big L times some overall. So what that's saying is that I have to sum over IJKL because big I, big J, big K, big L are all located here and here, right? So that means that actually I didn't write it, but out front here we have the sum, the sum, the sum, the sum over I, J, K, and L. Now, there's a couple interesting things that the result here never sees big I, J, K, or L. So these are sometimes these larger ones that I created here. And I could have put anything in there because they don't appear over here. Only small I, small j, small k, small l show up over here. They're called dummy indices, which is, of course, not very nice, but um, they are called dummy because they're only temporarily there and then they disappear later. And so these are dummy variables. Now, even though these are dummy, these quantities are very real, right? Remember over here, this is the proportionality between a force and a displacement, right? So same thing here. This could be some sort of thing that we're talking about that's physical. The reason I'm not calling it a force necessarily is because this could be that I'm trying to get a transformed um, elastic matrix. So for example, this could be an elastic matrix in one crystal system with, in one system with x1, x2, x3 in a particular way. And then I actually shift it into I have to change coordinates because I've got some sample where I sliced it out of a different orientation. And so now I want to transform that into a different coordinate system. And so I have these four, we'll derive this actually, that we'll need four transformation matrices here, right? And then we'll get our final result. But in the transformation, these are very real transformation matrices. And this is a very real tensor with, let's say, elastic constants in it. So even though the subscripts are dummy. It's just because you have to use them to cycle through in order to get the final result. Okay? So that's the beginning of our tensor notation. So make sure that you're comfortable with this, and then we'll move on.